So in our last section of chapter 4, we're going to talk about binomial and geometric probability distributions. The first one we're going to talk about is the binomial distribution. So there's a lot of experiments and situations that result in what are called dichotomous responses. So those are responses for which there exists two possible choices, such as true, false, yes, no, defective, non-defective, male, female, etc. A simple example of this is tossing a coin, where there's only two possibilities, heads or tails. And there's a lot of other types of experiments similar to a coin toss, where you're observing the success or failure of a certain outcome. And such experiments give us a probability distribution called a binomial distribution. There are 4 conditions that an experiment has to meet in order to be considered binomial. Obviously, the first one is that it falls into one of two categories, success and failure. Now, it is important to recognize that success doesn't necessarily have to be a positive, because if, for instance, we're looking at the number of people who get colds after being doused with water, success might be defined as getting a cold, and failure would be they don't get a cold. There has to then also be a fixed number of n observations. So you have to be dealing with a specific sample size is another way of thinking about it. The third thing is that these observations are independent, which means knowing the result of one observation tells you nothing about the other observations. And the last one is that the probability of success has to be the same for each observation. So 3 and 4 are very much tied together, because if observations aren't independent, then the probability is not the same for each observation. So if you answered no to either 3 or 4, the other one will also be no. So if 3 is no, 4 will obviously be no, and if vice versa. So let's go ahead and look at some examples where we are going to determine if something is a binomial. So the binomial distribution is the distribution of the count of x successes in our binomial experiment with parameters n and p, where n is your outcome and p is your probability. And then the possible values of x are always the integers starting from 0 all the way up to whatever your sample size is, n. So in our first example, we have that we are tossing 20 coins and counting the number of heads. So we want to check to see if our first condition is met, and that is that there are 2 outcomes. And because we're counting heads on a coin, we can get heads or tails. So there are 2 outcomes. The second is that we have a fixed number of trials. And because we are flipping this coin 20 times, n is 20, that is our number of trials. For 3, we have talked about this multiple times. Coins are always independent. So we are good there. And then also, because this is a regular coin, our probability each time we flip it is 1/2. So that tells me that this is a binomial distribution. Our next 3 examples are going to have to do with cards, and we're going to slightly change the wording of the problem each time to see if it stays a binomial distribution. So for our first example, we're picking 5 cards from a standard deck and counting the number of hearts, and we're going to replace the card each time and reshuffle. So for our first one, if we are looking at only 2 outcomes, this is technically only 2 outcomes, because even though there's 4 suits, we're looking specifically at hearts. So when I draw my card, it's either going to be heart or not. So our outcomes are hearts or not, no hearts. So from that aspect, it is only 2 outcomes. For 2, we are only picking 5 cards, so n is 5. If it hadn't specified, it's still always going to have a set number of outcomes, because there's only a certain number of cards in a deck anyway, so there's always going to be a specific sample size. For number 3, for the trials being independent, the key things that kind of lead us to knowing that these are independent is that we're replacing the card each time and reshuffling. That's very important words here. So because of that, we are meeting the independent. And that is also how we are also meeting our probability remaining the same, because we're replacing the card. So because there are 13 hearts in a deck, our probability is 1/4 each time. So all 4 conditions are met, so this is also a binomial distribution. In our third example, we're still picking the 5 cards and counting the number of hearts, but now we're not reshuffling. So our first 2 conditions are still met. So we don't have to worry about hearts and the n equals 5. We just have to check 3 and 4. And the key thing here is that we're not reshuffling. So even though we're returning the card to the deck, because we're not reshuffling, we now know where that card is. If we put it back on the top or we put it back on the bottom, it therefore changes it to no longer be independent, and the probability is not going to remain the same anytime. So P is not 1/4. So this is no longer a binomial distribution. And the last time, we're just choosing a card from a standard deck until you get a heart. So here it says until you get a heart. So even though a deck of cards has 52, and we're just like, well, there's always going to be a specific sample size, here, because we're not saying a fixed number of trials that we are looking at, we've actually violated the fact that n is no longer 5. Because if I said, like, we're going to go through like 10 cards or even 15 cards, or if I said I'm going to pick 52 cards, shuffle each time, and figure out how many of them are hearts, you would expect you would get 13 hearts, but you're not guaranteed. So because it says until, we no longer have a fixed n. So no longer have a fixed n. We also we're not returning the card, and we are also not reshuffling each time. So we also have an issue with those 2 conditions as well. So this is not binomial. So now let's talk about how we calculate our binomial probabilities. So suppose we're going to talk about this through an example. So we have Calvin. He's going to take a 5-question true-false quiz for which he is not prepared. So he's going to be guessing on all 5 questions. So we want to know the probability he gets all of the answers correct, he gets all of the answers wrong, he gets exactly 3 answers correct, and he will pass the quiz. So we're going to talk about how this works if you don't use the rules for binomial, and then we'll talk about the binomial formula. So if we think of this as a probability distribution, so a regular probability distribution like we did in section 3, C would be a correct answer, W represents a wrong answer. So we're going to list all of the possible combinations of correct and incorrect responses and make a distribution. So if you think about it like the question where we did the flipping a coin and we were looking at the number of heads, it's very similar in that aspect. So our row across the top, X, we can have that x equals 0, because you can get none of them right. We can then have x equals 1, and we can go all the way up to x equals 5. I'm gonna leave a little bit room in here to do the work, and then across the bottom here, I'm gonna do the probabilities. I'm gonna leave some room in the middle to talk about the outcomes. So if we think about how many ways there are for him to get none of them correct, so that would mean all 5 of them are wrong. So there is only one way for that to happen. So I'm gonna just keep a numerical count along the bottom. I'm also gonna do all 5 correct first. So there's also only way for him to get all 5 of them correct. So that would just be 5 C's. So there's also only one way for that to happen. But the 1, 2, 3, and 4 are gonna have multiple ways for it to happen because it could be any of the 5 questions he gets correct. So if he gets one of them correct, it could be the first one and then the next 4 are wrong. Or he could get the second one correct and the next 3. He get first 2 wrong, third one correct. He could get the fourth one correct, or he could get the first 4 wrong. Ooh, too many loops. And the last one correct. So there are 5 ways for him to get one question correct. So if we do then 2 questions correct, it's very similar. He get the first 2 correct and then the next 3 wrong. Or it could be first one correct, last one correct. First and then the next 2. I'm not going to do all of them, so that's only 5 of them. There actually are 10 total. So if you think of all of the different possible ways, you could place those 2 correct ones, first 2, last 2, the first and the last, the middle 2. Just take my word for it, there's 10 ways. It also is the same with 3 correct. So like you could get the first 3 correct and 2 wrong, or the first wrong, the last 3 correct, correct, wrong, correct, wrong, correct, and it keeps going. So there are also 10 ways for that to happen. To get 4 of them correct, it could be the first 4 and the last one, the last 4, it could be the second one that's wrong. He could just get the third one wrong, or he could get the fourth one wrong. So there's 5 ways for that. So if we now think probability, I need to figure out how many total outcomes there are. And there are 32 total outcomes. So if you do 1 plus 5 plus 10 plus 10 plus 5 plus 1, that gives you 32. So the probability is 1 out of 32, 5 out of 32, 10 out of 32, 10 out of 32, 5 out of 32, and 1 out of 32. Now that I have created basically a probability distribution, I can now answer the question. So the probability he gets all of the answers correct is the probability that x equals 5, which is just 1 out of 32. Probability he gets all of them wrong is the probability that x is 0, which is also 1 out of 32. The probability he gets exactly 3 correct would be the probability that x is 3, which we know is 10 out of 32. And then the probability he passes the quiz. So a passing score on a 5-question quiz is at least 3 out of 5. Because a 3 out of 5 is a 60%. So if he gets a 3 out of 5 or higher, he passes. So that's the probability that x is greater than or equal to 3. So we do 10 out of 32 plus 10 out of 32 plus 1 out of 32. Sorry, 10 out of 32 plus 5 over 32 plus 1 over 32. So that's going to be 16 over 32, which is 1/2. So there's a 50% chance that he passes the quiz. So there is another way to do this, and this one involves a formula. So it can be super time consuming, especially if your sample size is larger, to create the probability distribution. So you think about how many possible ways are for each of these outcomes to happen. So if we think back to what we did before, we have talked about combinations. So the formula for calculating a binomial probability actually uses combinations. So if you have the same probability P for each observation and at your set sample size N, the formula, so the probability that X equals K is NCK times the probability raised to the power of K times 1 minus P to the exponent of N minus K. So the way the formula works is the probability X equals K represents the probability of K successes. So you're talking about how likely is it I am to get this many correct. NCK takes care of all possible combinations of this happening. So it's the combination of K successes in N trials. P to the K is then your probability of success raised to the number of successes. And then 1 minus P to the N minus K is your probability of failures raised to the number of failures, which is where the N minus K comes from. That's our number of failures. Now, there is a way to do the combinations in the calculator. So to cut down on the amount of time it takes you to use this formula, I don't expect you to do that factorial every time. So remember, NCK is going to be N factorial over K factorial times N minus K factorial. And I don't need you to do that work every time. So on your calculator, if you hit math, and then you want to go over to either, depending on your calculator, it's going to be PRB or PROB. And then you want number 3, and it says NCR. That will allow you to do a combination in the calculator without having to write out the factorial. So N is your number of trials. K is your number of successes. And P is your probability of success. So now we want to recalculate some of the probabilities that we did previously, but now we're going to use the formula instead of the table. So if I wanted the probability Kelvin gets exactly 3 correct, so the probability that X equals 3, we're going to do 5C3 times, and then because it is a multiple choice quiz, so that is true, false. So that means there's only 2 outcomes. So that means the probability of success is 1/2. So we'll do 1/2 to the third because he's getting 3 correct. And then we're going to do the probability of failure. So 1 minus 1/2, which is also 1/2. And then the amount he gets incorrect, which in this case is 2. So if you do this all in the calculator, 5 choose 3. So that gives you 10 times, and then 1/2 to the third is 1/8. 1/2 squared is 1/4. And you get 5/16. We had 10/32 when we did it, and I didn't simplify it, but 10/32 is 5/16, so it is the same. If we do similarly, what's the probability that Calvin will pass? So the probability that x is greater than or equal to 3. Now you would have to do this as multiple steps, because I have to do the probability that x is 3 plus the probability that x is 4 plus the probability that x is 5. So it means doing the formula 3 times. We already know the probability that x is 3. That's the 5/16. But then I would have to do 5c4 times 1/2 to the 4th times 1/2 to the 1st. And then I have to do 5c5 times 1/2 to the 5th times 1/2 to the 1st. So I have to do my remaining probabilities. So then I have 5/16, and then 5c4 is 5, and then 1/2 to the 4th is 1/16 times 1/2, plus then 5c5 is just 1, and then 1/2 to the 5th is 1/32, and then this should actually say 1/2 to the 0, which is just 1. So then we get 5/16 plus 5/32 plus 1/32, which if you do in your calculator, because they don't have common denominators, you end up with 1/2, which is exactly what we got before. So definitely a lot less time than having to create the probability distribution table and then finding all of the possible outcomes. You can just use combinations and then probability. Because they're independent, you can multiply the probability of successes together and the probability of failures together. Now, as we saw, the probability when I did a greater than or equal to, you have to add each probability independently. And depending on what that inequality is, it can be super time consuming. So there is a way to do greater than or equal to, or you can do the inequality probabilities on the calculator using binom CDF. So if you hit second and then vars, and then you go to the letter B, which is towards the bottom, it's binom CDF. And then all you need are N, which is your number of trials. You need your P, which is your probability of success. And then you need what they call your X value, which is your number of successes. It's what we call K, but in the calculator, they call it the X value. So you need those 3 things. So CDF represents the cumulative distribution function. And so it wants an interval. Now here's the thing, binom CDF can only do less than or equal to. So if you are doing a greater than or equal to, or even a greater than or less than, you have to rewrite it as a less than or equal to probability function first before you can use binom CDF. So we're going to talk about some ways you can write that, and we'll do some examples in the calculator. So if we have a binomial distribution that has a probability of 0.4, and we're looking at 5 trials, and we want to find the probability that X is greater than or equal to 1. Less than or equal to 1, I should say. So we know that N is 5, P is 0.4, and in this case, K is 1. So I can do that directly into binom CDF. So I can do binom CDF, and then it would be 5, 0.4, 1. And it's going to give me my decimal, which is 0.33696. If you wanted to, you could also round it to 0.337. Because if I wanted to round 4 decimal places, it ends up being 337. If I then look at the probability that x is less than 3, I have to change that to a less than or equal to. So the probability that something is less than 3 is the same thing as saying the probability that it's less than or equal to 2. Because everything less than 3 is 0, 1, and 2. So now n is still 5, p is still 0.4, but now k is 2. So we do binom CDF, and then we have 5, comma, 0.4, comma, 2. And we get 0.68256, which you can also round to 0.6826. So less than or equal to and less than are probably the easiest ones to do because they're pretty straightforward. Like one of them is just do binom CDF. The other one is just to make it one number less, and that's your equal to. The harder ones are the greater than and the greater than or equal to, because you have to think about it as you have to switch it to a less than or equal to, which involves 1 minus. So if I want to look at everything greater than or equal to 4, another way to think of it is it's 1 minus everything else. So it becomes 1 minus the probability that x is less than or equal to 3. So, because if you think it's either greater than or equal to 4 and everything else is less than that. So if I do 1 minus everything less than that, the remaining part is everything that's greater than or equal to. So my calculator, if I do 1 minus binom CDF with my n of 5, my p of 0.4, and my k of 3, and you can do 1 minus in the calculator, and then do the binom CDF. We get 0.08704, which you can also write as just 0.087. The hardest one might be just greater than, because when you do greater than, it depends, you have to do 1 minus the probability. This one you can, when I switch it to a less than or equal to, I'm actually going to keep the number 4. Because I'm not including 4 in my answer, when I switch it to a less than or equal to, because I haven't included 4 already, I have to include it for my less than or equal to. So it becomes 1 minus binom CDF. And then we have 5, comma, 0.4, comma, 4. Which is going to give us 0.01024 or 0.0102. This last one is also really weird because I only had 5 trials. The only thing greater than 4 is technically 5. So you could have also thought of this one as just the probability that x equals 5. Okay. So the next thing we're going to talk about is how to find the mean and standard deviation for a binomial distribution. And it's probably actually the easiest formulas for mean and standard deviation. So the mean for a binomial distribution is just to take n times p. So however many trials you have, multiply it by the probability, that gives you your mean. Your standard deviation is then calculated as the square root of n times p times q, where q equals 1 minus p. And then you've got to remember that 1 minus p is your number, so this is your number of failures. So it's the square root of your sample size times your number of successes times your number of failures. So let's go back to Calvin's quiz. So if we want to find the expected value, which is just another way of saying mean, and the standard deviation for Calvin's quiz, and then we're going to interpret them. So first, his expected outcome. So there are 5 questions. Probability is 1/2. half of 5 is 2.5. And then for our standard deviation, we're going to do the square root of 5 times 1/2, and then our failure is also 1/2. And that gives us 1.118. So if I'm interpreting this, we can say if Calvin took the quiz many times, he is expected to get 2.5 questions correct. Now, even though that doesn't make sense because you can't really get half a question correct, we always want to interpret the mean and standard deviation for these using the decimal. We don't actually want to round it. We want to use the decimal. So then if I'm interpreting my standard deviation, we would say the typical deviation from the expected value is 1.118, and then questions correct. Let's take a look at another example. So we have that the probability that any random freshman girl will agree to go with Nick to the senior prom is 0.1. Suppose Nick asks 20 random freshman girls to the prom. What is the probability that exactly one will say yes? At least one will say yes. And then on average, how many freshman girls will agree to go with Nick to the prom? And then what the standard deviation is. So X here represents the number of girls who say yes. So we're going to start with the probability that X equals 1. So that's going to be 20C1 times, and then because the probability that someone says yes is 0.1, it's 0.1 to the first power times, so the probability that they don't say yes is 0.90, and that would be to the 19th. So if I do 20C1 in my calculator, that's 20 times 0.10 times, and then 0.9 to the 19th is a very, very not fun decimal, so I'm just going to leave it as 0.9 to the 19th, and so I can just do 20 times 0.10 times 0.9 to the 19th, and we're going to get 0.2702. So there's about a 27% chance that one girl says yes. If I want to find the probability that at least one says yes, so that's the probability that X is greater than or equal to 1. If I change that to a less than, that's the same thing as saying 1 minus the probability that X equals 0. Because if I don't have any girls say yes, then the remaining have to say yes. So we'll do 1 minus 20 to 0 times 0.10 to the 0 times 0.90 to the 20th. And remember, any number, choose 0 is always 1. And then 0.10 to the 0 is also 1. So I'm just doing 0.90 to the 20th. I'm doing 1 minus 0.90 to the 20th. So that's going to be 0.8784. So there's a very good chance at least one girl says yes to Nick. So for our mean, our expected value, we have 20 times 0.10 So that means we expect 2 girls are going to say yes out of the 20. And then our standard deviation is the square root of 20 times 0.10 times 0.90. Which is 1.342. So the typical deviation from the number who say yes is 1.342, which is actually pretty high since the mean is 2. So the last distribution we have to talk about is the geometric distribution. In a geometric distribution, the wording is slightly different. So in a geometric, we look at the number of trials until you get the first success. So a binomial, we usually use the letter X to denote a binomial distribution, and it's the number of successes in a fixed number of trials. But a geometric usually uses the letter Y, and it's the number of trials until you get the first success. So kind of some examples of how this is worded is flipping a coin until you get heads, rolling a die until you get 6, throwing darts at a dartboard until you hit the bullseye. That fourth example that we did at the beginning where it said was drawing a card from a deck until you get a heart, that's an example of a geometric distribution. So there are things that are the same to a binomial distribution. There are a couple that are different. So one of the things that is the same is that it is binary. So similar to a geometric distribution, each trial can only have 2 possible outcomes, success or failure. It also has independence. So the trials in the experiment have to be independent. The next one is where it's different. So instead of having that set number of trials, we now have trials until the first success. So the variable of interest is the number of trials required to reach the first success. And then the other one is the same. So this probability of success, still has to remain the same from trial to trial. So 3 of the 4 requirements for a geometric distribution are the same as a binomial distribution. It's just the trials that are differently. So instead of looking at a fixed n, we're looking at the trials until the first success. So the way we're going to kind of get to our geometric probability formula is very similar. We're going to look through an example. So if we roll a 6-sided die, and Y is going to be the number of trials until you roll a 6. So if I look at the probability that you roll a 6 on the first trial, so there's 6 outcomes on a die. The probability that the first one is a 6 is just 1 out of 6. The probability that you roll another number on the first trial, but a 6 on the second trial. So there are 5 numbers that aren't a 6. So the probability that the first roll is something other than a 6 is 5 out of 6. Times, and then 1 out of 6. So that's going to give us 5 over 36. If we roll another number on the first 2 trials, but a 6 on the third, we have 5 out of 6 times 5 out of 6, and then times the 1 out of 6. So that's going to be 25 over 216. So if I were to kind of sum this up in a table, so we have Y and we have probability of Y. So we had 1, 2, and 3. We could keep going, but 1 was 1/6, then we had 5/36, then we have 25 over 216, and then we could technically keep going if we wanted, right? We could say what's the probability it happens on the 4th or the 5th. So one thing to think of is, can Y be 0? And in this case, the answer is no. And the reason is that because you are looking at successes, you have to have at least one trial with a success. The next thing is, if we were to look at a table, when do you stop? And the answer is never. You could keep going forever without a success. Now, eventually your probability is going to get so small that it's practically zero, which is unlikely that you're going to have one that goes on forever. But there's a reason why we don't do distribution tables for geometric, and that's because technically they go on forever. So if we're kind of looking at the pattern, we had 1/6, and then we had 5/6 times 1/6, and then we had 5/6 times 5/6 times 1/6. If we're looking at a pattern, it's your number, it's your probability of failure, which was the 1 minus p, and then it was that many failures as an exponent times p, which is your success. And that's kind of how we get our geometric probability formula. So for the formula, you have 1 minus p, which is your probability of failures. Your exponent is then k minus 1, which is your number of failures. And then p is your single success. So the probability y equals k is your probability of success on the kth trial. 1 minus p to the k minus 1 is your probability of failure raised to your number of failures. And then lastly, we have p, which is our single success, because you're always only going to have one success. Unlike a binomial distribution where you could have multiple successes or no success, in a geometric, you only ever have one success and the rest are failures. So if we go back to that example where we're talking about rolling a die until you get a 6, if we want to know the probability that it takes 5 rolls until you get a 6, so that's the probability that y equals 5. So that would mean you have 4 failures. You have 5/6 to the 4th times 1/6. Now these you're probably going to want to write as decimals, because depending on your probability, the number of failures you get, that probability is going to be that's going to be a fairly large fraction, I guess I should say, with a fairly large denominator. So these we typically will write as decimals. So it's going to be 0.0804. If you wanted to write it as a fraction, you could, but it's 625 over 7776. So I don't typically write these as fractions just because the denominators get really, really large. I will typically always just write them as decimals. So the next one, what is the probability it takes you 10 rolls to get a 6? So that's the probability that y is 10. So that means you had 9 failures, so 5/6 to the 9th times 1/6. And it is probably best to just do all of this in a calculator at once instead of like doing it in steps. And we're going to get 0.0323. And then we can also do inequalities with binomial distributions. So if we want to know the probability that your 6 happens within 3 rolls. So that's the probability that y is less than or equal to 3. So that means that it could happen on your first roll, your second roll, or your third roll. And we did already calculate all of these probabilities independently on the previous page. So the probability it happens on the first roll was 1/6, plus the probability it happened on the second roll was 5/36. And then the probability it happened on the third roll was 25/2/16. So if we add all of these fractions in our calculator, we're going to get 0.4213. And then the last one, what is the probability that it takes at least 4 rolls to get a 6? So that's the probability that y is greater than or equal to 4. Now for geometric distributions, because there is no end, anytime you have a greater than or equal to inequality, you always want to change it to a less than or equal to, because there's no way for me to add everything greater than or equal to 4 because I have no end. So everything greater than or equal to 4 is the same thing as 1 minus the probability that y is less than or equal to 3. And we already calculated the probability that y is less than or equal to 3. So we're going to do 1 minus 0.4213, which is going to give us 0.5787. So just like you can do a binomial inequality on the calculator, you can also do geometric the geometric inequalities on the calculator. So if you go to second vars and then you go to the letter F, that's Geomet CDF. So the things you need for this are your probability, so that's your P, and then your X value, which again is your number of trials until the first success. So also your K. So Geomet CDF P comma K, it always computes the probability that y is less than or equal to K. So again, you always want to, you convert it to a less than or equal to inequality the exact same way as you did for a binomial distribution. Okay. The last thing we have to talk about are the mean and standard deviation for a geometric random variable. So their formulas also very easy compared to normal mean and standard deviation formulas. So our mean, or the E of y, is 1 over P. So it's just 1 over the probability. And that gives you the number of trials you expect to run before you get your first success. And then the standard deviation is the square root of Q over P. So remember, Q is 1 minus P, and it represents your probability of failures. So you do the square root of the probability you fail divided by your probability of success. So that's the typical, if you're doing interpretation, it's the typical number of trials that deviate from the mean. So we're gonna look at one last example. So to start her old lawnmower, Iris has to pull a cord and hope for some luck. On any particular pull, the mower has a 20% chance of starting. So we want to find the probability that it takes her exactly 3 pulls to start the mower. So that's the probability that y equals 3. So that means she had 2 failures. So if there's a 20% chance of it starting, that means there's an 80% chance that it doesn't. So 0.80 to the second power times the 0.20, which is going to be 0.128. Next, we want to know the probability it takes her more than 10 pulls. So that's the probability that y is greater than 10. So that becomes 1 minus the probability that y is less than or equal to 10. So when I do because it says specifically more than 10, I have not included 10 yet. So when I do it in my calculator, I have to do the probability that y is less than or equal to 10. And I am going to use the Geomet CDF here because I don't want to do 1 plus all of the probabilities for 1 through 10, that would take a while. So your P is 0.20, and then you would do comma 10 for K. And we're gonna get 0.1074. So about 11% chance that it takes more than 10 pulls. And then the last one, how many pulls do you expect it will take Iris to make? So that's the mean. So my E of Y, which is just 1 over my probability, which is 0.20, which is 5. So if I were interpreting this, I would say we expect Iris to make 5 pulls before the mower starts. So different than the interpretation for a binomial distribution, where it was specifically talking about how many successes you're going to get in your number of trials. This one is how many trials you're actually going to have to perform to get your first success. So a little bit different in the interpretation for a geometric distribution than a binomial. Please reach out with any questions you might have about binomial or geometric distributions, especially when it comes to the formulas and how you might want to use the calculator.